Tonight, we're going to look into something that most people assume is absolutely nothing. The dark, silent abyss that separates one galaxy from another. From Earth, it looks like an unbroken ocean of black between every shimmering island of stars. But here's the strange truth. That darkness isn't empty. It's filled with something. Not stars, not planets, not anything you've ever seen with your eyes. There's a hidden architecture out there. Invisible threads of gas, plasma, radiation, and an unseen scaffolding holding the entire universe together. And by the end of this journey, you're going to understand what really fills the spaces between galaxies and why those seemingly empty gaps might be the most important regions in the entire cosmos. Before we go any deeper, if you enjoy these slow, thoughtful explorations of space, a quick like or subscribe really helps this channel keep growing. It's a small gesture on your end, but it makes a real difference on mine. Now, let's begin. When you look up at a clear, dark sky, your eye sees a few thousand stars at most. A handful of fuzzy patches if your vision is sharp. Maybe the pale ribbon of the Milky Way arching overhead. And between all of those points of light, blackness. A deep, total blackness that seems to swallow everything. Most people, if you ask them what fills that blackness, would shrug and say nothing. Empty space. The void. And in a way, they would be more right than they realize. But also, in a much more interesting way, they would be completely wrong. Because the spaces between galaxies, the enormous chasms separating one swirling island of stars from the next, are not empty. They are some of the strangest, most diffuse, most surprisingly active environments in the entire universe. And what fills them is something so thin, so faint, so bizarre by human standards that for decades astronomers literally could not find it. Half of the ordinary matter in the universe was missing. We knew it had to exist. The math demanded it. The Big Bang demanded it. But when we counted up all the stars and all the gas inside all the galaxies, the numbers did not add up. Trillions upon trillions of tons of matter were unaccounted for. And it took new telescopes, new techniques, and a kind of cosmic detective work spanning more than half a century to finally figure out where it had been hiding all along. It was hiding right there in the dark, in the spaces we thought were empty. To understand what intergalactic space really is, we first have to be precise about what the word means. The prefix inter just means between. So intergalactic space means space between galaxies. That sounds simple enough. But the distinction matters because there is another kind of space that gets confused with it all the time. Interstellar space. The space between stars within a single galaxy. These two environments are not the same thing. They are not even close to the same thing. And the difference between them is one of the keys to understanding the true emptiness and the true richness of the cosmos. Inside a galaxy like our Milky Way, the space between stars is not really empty either. It is filled with what astronomers call the interstellar medium. Thin clouds of gas, mostly hydrogen, scattered grains of dust, faint streams of charged particles, and the occasional dense pocket of cold molecular gas, where new stars are slowly being born. The density varies wildly depending on where you are. In the cold molecular clouds, you might find 1 million particles per cubic centimeter. That sounds like a lot, but for comparison, the air you are breathing right now contains roughly 25 quintillion molecules in that same tiny volume. Even the densest interstellar cloud is millions of times thinner than what we would call a hard vacuum on Earth. In the more typical regions between stars, far from any nebula, the density drops to about 1 atom per cubic centimeter. One single atom. In the volume of a sugar cube. That is the air, so to speak, that fills most of the space between the stars in our galaxy. Now hold that number in your mind. 1 atom per cubic centimeter. Because we are about to leave the galaxy entirely. We are about to step out beyond the spiral arms, beyond the halo of old stars, beyond even the diffuse cloud of dark matter that surrounds the Milky Way. And we are going to enter the deep void between galaxies. And out there, the density does not just drop, it plummets. In the vast spaces between galaxies, the typical density of ordinary matter is something like 1 atom per cubic meter. Per meter, not per centimeter. That is a difference of a factor of 1 million. If interstellar space is thin, intergalactic space is essentially nothing. If you took a volume the size of an average bedroom and you placed it out there in the deep cosmic gulf, you might find a few dozen lonely hydrogen atoms drifting through it. Sometimes fewer. The best vacuum chambers humans have ever built on Earth, the ones used in advanced physics experiments, still contain millions of times more particles per cubic meter than the average region of intergalactic space. We literally cannot recreate that level of emptiness in any laboratory. The universe out there is emptier than any vacuum we know how to make. And yet, here is the strange and wonderful thing. Even at 1 atom per cubic meter, when you start adding it up across the unimaginable volumes of space between galaxies, the total amount of matter becomes staggering. The universe is mostly empty, but mostly empty multiplied by a volume large enough to contain trillions of galaxies still adds up to an enormous quantity of stuff. In fact, when astronomers carefully account for everything, the matter floating in the spaces between galaxies vastly outweighs the matter inside galaxies. The stars, the planets, the gas clouds, the dust, all the bright glowing material that we think of as the universe, that is the minority. The majority of ordinary matter, the regular protons and neutrons and electrons that make up everything familiar, is not inside galaxies at all. It's out there, drifting in the dark, in clouds so thin you would never notice them. This is one of the most counterintuitive facts in all of astronomy. When you look at a picture of the cosmos, your eye is naturally drawn to the bright spots, the galaxies, the nebulae, the glowing arms of spiral structures. It feels like that is where everything is, but it is not. The bright spots are just the visible decorations. The real bulk of ordinary matter is spread out in the dim spaces in between, almost invisible, but enormous in total quantity. For a long time, we did not know this. For most of the 20th century, astronomers were quietly aware of a deeply uncomfortable problem. They had a very good understanding of how much ordinary matter the universe should contain. The Big Bang model, supported by extraordinarily precise measurements of the cosmic microwave background, and the abundance of light elements like hydrogen, helium, and lithium, told us with great confidence how many baryons, the technical name for ordinary particles like protons and neutrons, were created in the first few minutes after the universe began. The number was not a guess. It was a tightly constrained prediction. And when astronomers went out and counted up all the visible matter they could find, all the stars, all the gas inside galaxies, all the warm clouds and galaxy clusters, they kept arriving at the same disappointing answer. They could only find about half of what should be there. The other half was simply missing. This became known as the missing baryons problem. And it was not a small discrepancy. We are not talking about a few percent here. We are talking about literally half of all the regular matter in the universe being unaccounted for. Imagine a banker doing the books and finding that half of all the money in the vault has vanished. Not stolen, just missing. Nobody can find it. That is the kind of mystery astronomers were dealing with. And for decades, nobody could solve it. To really appreciate how strange this situation was, you have to understand just how confident astronomers were in the prediction. The Big Bang model is not some loose framework. It is one of the most rigorously tested theories in all of science. In the first 3 minutes after the universe began, while everything was still extraordinarily hot and dense, nuclear reactions were taking place across all of space, fusing protons and neutrons into the lightest atomic nuclei. The exact ratios of hydrogen to helium to lithium that emerged from those first 3 minutes depended sensitively on how much ordinary matter the universe contained. Too much matter and you would end up with too much helium and not enough hydrogen. Too little matter and the ratios would skew the other way. By measuring the actual ratios we observe today, in the oldest, most pristine clouds of gas in the universe, astronomers could calculate backward and figure out exactly how much ordinary matter had to have been present at that moment. The number was precise. It was repeatable. It came out the same regardless of which technique you used to measure it. And then, when astronomers looked at the universe today and counted up all the stars and gas they could find, the answer was off by a factor of 2. Not by a few percent, by a factor of 2. It was as if the predictions of nuclear physics, confirmed by every other test, were saying the universe contained twice as much ordinary matter as we could actually see. Either the predictions were wrong, which seemed nearly impossible given how many other things they got right, or the matter was real and we just could not find it. Most astronomers reluctantly came to accept the second possibility. The matter had to be out there, somewhere, hiding. Now, before we go further, it is important to be clear about what this missing matter is not. It is not dark matter. Dark matter is a completely separate puzzle. Dark matter makes up about 85% of all the matter in the universe, when you count only matter and ignore dark energy. It is some kind of mysterious substance that does not interact with light at all. We know dark matter is there because of its gravitational effects, but we do not know what it is made of. The missing baryons problem is different. It is about the ordinary matter, the stuff we do understand, the stuff we are made of. We knew exactly what it was. We just couldn't find where it had gone. The first real clue came in the late 20th century, when astronomers started thinking more carefully about the temperature of the gas in intergalactic space. Inside galaxies, gas tends to be relatively cool. It can collapse and form stars, but out in the vast spaces between galaxies, the gas can be heated to extraordinary temperatures by gravitational shocks, by radiation from quasars, and by the slow gravitational pull of large-scale cosmic structures. Astronomers began to suspect that much of the missing ordinary matter was hiding out there in the form of an extremely hot, extremely thin plasma, a gas heated to temperatures of hundreds of thousands or even millions of degrees, but spread so thinly across such enormous volumes that it was essentially invisible to ordinary telescopes. They gave this hypothetical material a name: the warm-hot intergalactic medium. Or, because astronomers love their acronyms, the WHIM and the WHIM, if it really existed, would solve the missing baryons problem in one elegant stroke. All those missing protons and neutrons, all that lost ordinary matter, would simply be drifting in the spaces between galaxies. Too hot to clump together, too thin to glow brightly, and almost impossible to detect with the instruments available at the time. The challenge then became, how do you find something so faint? How do you look for matter that emits almost no light, that is spread so thinly that any single cubic meter contains barely anything at all? The answer required a combination of clever physics and patient observation. When extremely hot gas is heated to millions of degrees, it does emit a faint glow. But that glow is not in visible light. It is in X-rays. And it is so dim that you need extraordinarily sensitive X-ray telescopes operating in space, above Earth's atmosphere, to have any chance of detecting it. Starting in the late 1990s and continuing through the early 2000s, X-ray observatories like Chandra and XMM Newton began to look for this faint glow, and bit by bit they started finding it. They saw warm gas in the spaces between galaxies. They detected hot plasma sitting in the gravitational valleys between galaxy clusters. The signals were faint, sometimes ambiguous, sometimes contested, but they were there. A more powerful technique came from looking at the light of distant quasars. Quasars are extraordinarily bright objects in the centers of remote galaxies, powered by supermassive black holes consuming enormous quantities of matter. From our perspective, they appear as brilliant points of light shining across billions of light years. And when their light travels toward us, it has to pass through everything in between, including the WHIM. As the quasar light passes through clouds of hot intergalactic gas, certain wavelengths get absorbed by atoms in the gas. By analyzing the spectrum of the quasar's light, astronomers can detect the chemical fingerprints of the matter the light passed through. It is a bit like shining a flashlight through a series of windows and being able to tell what each window was made of just by looking at the shadow of the light on the other side. Using this technique, astronomers found absorption signatures of oxygen, of carbon, of other elements, all sitting in the deep spaces between galaxies. Real evidence that the missing baryons were there. By around 2020, after years of accumulating data from multiple instruments and multiple techniques, the case had become strong enough that most astronomers consider the missing baryons problem essentially solved. The matter was where the WHIM model predicted it would be, drifting in the dark, hot, thin, and almost invisible, but undeniably there. Let me try to give you a sense of how one of these quasar absorption measurements actually works, because it is one of the more beautiful pieces of physics in modern astronomy. Imagine a single photon of ultraviolet light, born in the brilliant accretion disk of a quasar maybe 10 billion light years away. That photon begins its journey toward Earth, traveling at the speed of light, crossing one cosmic filament after another, passing through cluster after cluster, weaving through the great voids between them. Along the way, it encounters atoms. Most of those atoms ignore it completely. The photon is at the wrong wavelength to interact with most of them, but every now and then, it passes near an oxygen atom that happens to be in just the right energy state. And in that brief encounter, the oxygen atom absorbs the photon entirely, swallowing its energy. That photon never reaches Earth. It is lost. Now multiply that single event by trillions. The light from a quasar contains photons at every wavelength, and those photons collectively pass through countless atoms during their long journey. By the time the quasar's light reaches our telescopes, certain very specific wavelengths have been thinned out, absorbed by the atoms in the intergalactic gas. When astronomers spread that light into a spectrum, they see dark gaps at exactly the wavelengths where atoms of oxygen, carbon, hydrogen, and other elements absorb. By measuring how dark the gaps are, they can calculate how many atoms of each element the light passed through. By measuring exactly where the gaps appear in the spectrum, accounting for the redshift caused by the expansion of the universe, they can even calculate how far away each cloud of gas was. A single quasar spectrum is, in this sense, a multi-billion year history of the matter that exists between us and that quasar. It is a ledger. It is a fossil record of the intergalactic medium written in absorbed light. This is how astronomers found the missing baryons. Not by seeing them directly, but by reading their shadows in the light of the most distant beacons in the cosmos. Every quasar in the sky became a kind of cosmic flashlight, and every flashlight beam carried with it a record of everything it had passed through. By analyzing thousands of these spectra, by patiently building up a statistical picture of what the intergalactic medium contained, astronomers were finally able to confirm that the missing matter was real, that it was hot, that it was thin, and that it was distributed in roughly the patterns the WIM model had predicted. The mystery that had haunted cosmology for decades was solved not by a single dramatic discovery, but by a slow accumulation of subtle evidence, photon by absorbed photon, spectrum by patient spectrum. So now, when you look up at the night sky and see those vast black gulfs between the galaxies, you can know some things that earlier generations of astronomers would have given anything to know for certain. Those gulfs are not empty. They are filled with a ghostly ocean of hot plasma, atoms of hydrogen and helium, and traces of heavier elements, all spread so thinly that you could fly through trillions of cubic meters of it, and never notice a thing. But over the unimaginable volumes of cosmic space, this ghost ocean adds up to more matter than all the stars and planets and visible gas combined. Let us pause and try to actually picture this, because it is hard to wrap your mind around. Imagine you could shrink yourself down to the size of an atom and float in the middle of intergalactic space. What would you see? Almost nothing. The nearest other atom might be tens of meters away. Maybe hundreds of meters. The blackness around you would be more empty than anything you could possibly imagine. There would be no air, no dust, no stars within reach. The nearest galaxy might be millions of light years away in any direction. And yet, every once in a great while, one of those distant atoms would drift past you, glowing faintly with its own thermal energy, heated by some long ago gravitational shock to temperatures that on Earth would vaporize anything we could build. The space around you would be both the emptiest and one of the hottest environments in the universe. a paradox of nothing and energy. Now zoom back out. Look at intergalactic space the way astronomers do, on scales of millions and billions of light years. From that perspective, those almost imperceptible whispers of matter start to add up into something coherent. They form vast diffuse clouds. They flow in slow currents driven by gravity. They settle into long stringy patterns. The ghost ocean is not uniform. It has structure. It moves. It has currents and pools and rivers. And those currents, as we are about to see, are not random. They follow the underlying geometry of the universe itself. But before we get there, it is worth dwelling for a moment on just how strange the physics of this environment is. On Earth, when we think about gas, we think about pressure and temperature in familiar ways. Gas in a balloon, gas in the atmosphere, gas pushing against the walls of a container. But the gas in intergalactic space behaves nothing like that. It is so thin that the atoms almost never collide with each other. They just drift along, each one essentially alone, traveling enormous distances before encountering another particle. The concept of temperature, which on Earth we associate with how fast molecules are bouncing around and bumping into each other, becomes a strange thing to apply to a gas where individual particles might wait thousands of years before meeting their next neighbor. The temperature of the whim, those hundreds of thousands or millions of degrees, refers to the kinetic energy of individual particles. Each atom is moving extremely fast, but there are so few of them, so spread out, that if you somehow stuck your hand into this million-degree plasma, you would not feel any heat at all. The heat is real, in the sense that the particles carry enormous energy, but the density is so low that it could not transfer that energy to anything of meaningful size. You would freeze long before you would burn. The vacuum of cold space would steal your warmth far faster than the rare hot particles could deliver any. This is one of those situations where our everyday intuitions about physics simply break down. The intergalactic medium is hot in a technical sense and yet would feel nothing like hot. It is matter, and yet it is so dispersed that it is closer to vacuum than to anything we would call a substance. It is almost a different state of being. A hovering, ghostly, attenuated something. Somewhere between presence and absence. And what is it made of? Mostly hydrogen. By far. Hydrogen is the simplest atom. A single proton with a single electron, and it has been the most abundant element in the universe since shortly after the Big Bang. Roughly 75% of all ordinary matter in the cosmos is hydrogen. The next most common is helium, at about 24%. Together, those two elements account for almost everything. Heavier elements like carbon, oxygen, nitrogen, iron, and so on, the ones that make up your body and the planet you stand on, account for less than 2% of the universe's ordinary matter. And in intergalactic space, those heavier elements are even rarer. They had to be forged inside stars and then scattered back into space by stellar winds and supernova explosions. So when we find traces of oxygen or carbon out in the deep void, we are essentially looking at the exhaust of dead stars from billions of years ago. Atoms that were once locked inside the cores of massive stars, fused under unimaginable pressures, then blasted out across the cosmos when those stars exploded, drifting outward into the great gulfs between galaxies, where they still float today, almost lonely, almost forgotten, but still detectable to our most sensitive instruments. Here's another thing worth understanding. The intergalactic medium is not static. It is not just sitting there. It is being constantly fed and stirred by what happens inside galaxies. Galaxies are not closed systems. They breathe. They throw off material into their surroundings through stellar winds, through supernova explosions, through the powerful jets that erupt from the centers of active galaxies, where supermassive black holes are devouring matter and shooting energetic particles back out into space at nearly the speed of light. All of this material, all this gas, all these heavy elements is steadily being expelled from galaxies and added to the intergalactic medium. At the same time, intergalactic gas is constantly falling back into galaxies, drawn in by gravity, providing the raw material for new generations of stars to form. There is a continuous cycle. Galaxies pull gas in from their surroundings. They use it to make stars. The stars eventually die and throw some of that material back out. Some of it stays in the galactic halo. Some of it escapes entirely, joining the deep intergalactic flows. And then, over hundreds of millions of years, some of that material may eventually fall back into the same galaxy or into a different one nearby, beginning the cycle again. This means the empty-looking space between galaxies is actually a kind of cosmic circulatory system. Is the medium through which matter flows from one structure to another. Without it, galaxies would slowly run out of fuel, unable to form new stars after the original supply was consumed. With it, they can be replenished, sustained, kept alive. The seeming emptiness is in fact the lifeblood of the visible universe. It just happens to be incredibly thin, incredibly faint, and incredibly difficult to detect. But here's the thing. Knowing that this gas is there is only the beginning of the story. Because once you accept that intergalactic space is filled with this ghostly ocean of hot hydrogen and helium, the next obvious question becomes, what shape does it take? Is it spread evenly throughout the universe, like a uniform sea? Or does it have structure? Does it pool in certain places and drain away from others? Does it follow some larger pattern that we have not yet appreciated? The answer, as we are about to discover, is one of the most extraordinary findings in all of modern cosmology. Because the matter between galaxies is not spread uniformly at all. It is organized. It flows along an unseen architecture, pooling in some regions and disappearing almost entirely from others. The galaxies themselves are not scattered randomly through the dark. They sit on the framework of something much larger. Something so vast and so intricate that when astronomers first began to map it, they could barely believe what they were seeing. And it has a name. It is called the cosmic web, and it is one of the largest known structures in existence. So we have established that the spaces between galaxies are not actually empty. They are filled with this ghostly attenuated ocean of hot plasma. Billions upon billions of tons of it, hiding in plain sight for decades, until our instruments finally became sensitive enough to detect it. And as we hinted a moment ago, the way that gas arranges itself across the cosmos turned out to be one of the most extraordinary discoveries in the entire history of cosmology. What astronomers found was a vast, intricate pattern stretching across the entire observable universe. A pattern so enormous, so beautiful, so strangely organic looking that when scientists first started to map it out, many of them struggled to find the right words to describe what they were seeing. It looked like a network. It looked like a nervous system. It looks, in the words of more than one astronomer, almost alive. This pattern has a name. It is called the cosmic web. And it is, by any reasonable measure, one of the largest known structures in existence, possibly the largest. It connects every galaxy to every other galaxy through threads of plasma and dark matter stretching across hundreds of millions of light years. It contains within it everything we can see when we look out at the night sky, and a great deal more that we cannot see at all. And to understand what fills the space between galaxies, you have to understand the cosmic web. Because in a very real sense, the cosmic web is what fills that space. It is the architecture of the universe itself. Let us start with how this discovery actually came about. Because the cosmic web was not something anyone predicted in advance. It emerged gradually over decades as astronomers began to map the three-dimensional positions of galaxies across larger and larger volumes of space. And the story of that mapping is itself one of the great quiet triumphs of modern science. For most of astronomical history, when scientists looked at the sky, they were essentially looking at a two-dimensional picture. They could see where galaxies appeared on the celestial sphere, their positions in the sky as projected from our vantage point on Earth. But they could not easily tell how far away those galaxies were. Two galaxies that appeared close to each other in the sky might actually be separated by billions of light years. One might be relatively nearby, the other unimaginably distant, just happening to lie in the same direction from our perspective. Without distance information, all the galaxies in the sky just look like a flat scatter of points. Patterns might be there, but they were impossible to see in 2 dimensions alone. The breakthrough came when astronomers got better at measuring distances using a technique called redshift. The basic idea is straightforward. The universe is expanding. As space stretches, the light from distant galaxies gets stretched along with it, shifting toward longer, redder wavelengths. The more distant a galaxy, the more its light has been stretched, and the larger its redshift. By measuring the redshift of a galaxy's light, astronomers can calculate roughly how far away it is. Combine that distance with the galaxy's position in the sky, and you suddenly have a 3-dimensional location for it. A real point in space, not just a smear on a flat picture. In the 1970s and 80s, astronomers began conducting what came to be called galaxy redshift surveys. The idea was simple but ambitious. Pick a patch of sky, point a telescope at it, and measure the redshift of every galaxy you could find in that patch. Then move to the next patch, and the next, until you had mapped the 3-dimensional positions of as many galaxies as possible across as large a volume of space as you could manage. It was painstaking, slow, repetitive work. Every single galaxy required its own measurement. Early surveys could only handle a few hundred or few thousand galaxies at most. But even those early surveys produced results that were almost shocking. Because when astronomers plotted the 3-dimensional positions of the galaxies they had measured, they did not see what they had expected to see. They had expected more or less a uniform random scatter. Galaxies sprinkled here and there throughout space, perhaps with some loose clustering in the densest regions, but mostly just spread out as a kind of cosmic dust. That is not what they found. What they found instead was structure. Real, clear, undeniable structure. The galaxies were not scattered randomly at all. They were arranged in long, stringy patterns. They formed walls and sheets. They clumped together at the intersections of these strings, forming dense knots. And between these strings and walls and knots, there were enormous regions of nearly empty space, vast bubbles of nothing. The galaxies seemed to be avoiding these regions, as if pushed aside by some invisible force leaving behind huge empty volumes surrounded by the thread-like structures where almost all the galaxies lived. This was not what anyone had been expecting. The universe, viewed at the largest scales, was not a smooth, uniform soup. It was a kind of foam, a network, a web, with matter concentrated along the threads of the web, and almost nothing in the bubbles between the threads. One of the first really striking maps of this structure was produced in the late 1980s by a team at the Center for Astrophysics in Cambridge, Massachusetts. The map showed a slice through space, with thousands of galaxy positions plotted as dots. And running across this map were features that had never been clearly seen before. Long curving filaments of galaxies, dense clusters where many filaments met, and one striking elongated structure that came to be known as the Great Wall, a sheet of galaxies stretching across hundreds of millions of light years, bounded on both sides by enormous empty voids. It was one of the largest structures ever detected up to that point, and it suggested that the universe had architecture on scales nobody had previously imagined. In the years and decades that followed, larger and more ambitious surveys took this work even further. The Sloan Digital Sky Survey, which began operations around the turn of the century, eventually mapped the three-dimensional positions of more than 1 million galaxies. Other surveys mapped millions more. As the data accumulated, the picture became clearer and clearer. The cosmic web is real. It is everywhere. It extends as far as our surveys have been able to reach, and it has the same general structure across the entire observable universe. Long filaments of galaxies surrounding vast voids, meeting at dense knots where the largest galaxy clusters live. Once you have seen these maps, you cannot unsee them. The universe is not a smooth, uniform sea of stars. It is a sprawling network of bright threads woven through enormous bubbles of darkness. The galaxies you can pick out as individual dots are arranged like droplets of water clinging to invisible strands of a spider's web. And the empty bubbles between the strands take up most of the volume of the universe, even though they contain very few galaxies of their own. To get a sense of the scales involved, consider some numbers. The largest filaments in the cosmic web stretch across hundreds of millions of light years. Some of them have been traced for more than 1 billion light years from end to end. The voids between them are similarly enormous. The largest known voids span hundreds of millions of light years across, almost devoid of galaxies, almost devoid of any visible matter at all. Within a typical large void, you might find only a handful of small galaxies scattered across a volume that could easily contain dozens of fully developed clusters in a denser region. The contrast between the filaments and the voids is extreme. The matter is concentrated. The emptiness is concentrated. There is very little in between. Now, why does the universe have this particular architecture? Why is the matter organized into filaments and voids rather than spread out smoothly? The answer takes us back to the very early universe, to the conditions that existed shortly after the Big Bang. Because the cosmic web did not just appear out of nowhere, it grew over billions of years, from tiny seeds that were planted when the cosmos was very young. In the first fraction of a second after the Big Bang, the universe was almost perfectly smooth. Matter and energy were distributed almost evenly across all of space, but not quite perfectly. There were tiny variations in density from place to place, microscopic fluctuations on the order of 1 part in 100,000. Some regions of space had ever so slightly more matter than average. Other regions had ever so slightly less. These differences were tiny, but they were real, and they were the seeds of everything that would come later. We can actually see these primordial fluctuations directly, in a way. When astronomers map the cosmic microwave background, that faint glow of radiation left over from the early universe, they find tiny temperature variations from one patch of sky to another. Those variations correspond to those original density fluctuations. The hotter spots in the microwave background were slightly denser regions of the early universe. The cooler spots were slightly less dense. So we have a baby picture of the universe, frozen in microwave light, showing us exactly what the seeds look like before they grew. And those seeds did grow. Slowly. Patiently. Over hundreds of millions, and then billions of years. Gravity took those tiny initial differences and amplified them. Regions of slightly higher density attracted more matter from their surroundings. As those regions accumulated more matter, their gravitational pull became stronger, allowing them to attract still more matter from even greater distances. Meanwhile, regions of slightly lower density steadily lost matter to their denser neighbors, growing emptier and emptier over time. This process did not happen uniformly. It happened along certain preferred directions, governed by the geometry of the initial fluctuations and by the way gravity collapses three-dimensional regions of space. When a slightly overdense region begins to collapse under its own gravity, it does not collapse into a point all at once. It collapses first along one axis, forming a sheet. Then it collapses along a second axis, forming a filament. Only at the very end does it collapse along the third axis, forming a dense knot at the center. This sequence, sheet to filament to knot, is the natural pattern of gravitational collapse on cosmic scales, and it produces exactly the kind of architecture we see in the cosmic web today. Vast sheets and walls of galaxies. Long filamentary strings stretch between them, dense clusters at the intersections of multiple filaments, and in between, the great voids, regions where the original density was just slightly below average, and which lost their matter to the surrounding overdense regions over the course of cosmic history. Computer simulations have been able to reproduce this whole process in stunning detail. By starting with a simulated universe that has those tiny initial density fluctuations, and then letting gravity act on it for billions of simulated years, scientists can watch the cosmic web grow. The simulations begin almost smooth, with just the faintest variations from place to place. Over time, those variations grow. Filaments begin to form, voids begin to open up, galaxies begin to cluster along the densest paths. And by the end of the simulation, after billions of years of gravitational evolution, you have a structure that looks essentially identical to the real cosmic web we observe in the actual universe. The same pattern of filaments and voids, the same kinds of clusters at the same kinds of locations. The match between simulation and observation is so good that it counts as one of the strongest pieces of evidence that we genuinely understand how cosmic structure formed. Now, here is where things become especially relevant to our story about what fills the space between galaxies. Because the cosmic web is not just about where the galaxies are located, it is about where everything is located. The hot plasma we discussed before, the warm, hot intergalactic medium, is concentrated along the same filaments. It pools at the dense knots where galaxy clusters live, and it largely drains away from the great voids, leaving them even emptier than the rest of intergalactic space. This means that the gas between galaxies has rivers and pools, just like water on the surface of a planet. The The cosmic web is, in a real sense, the river system of the intergalactic medium. The filaments are the streams along which gas flows. The clusters are the lakes where gas accumulates. The voids are the dry deserts where almost no gas exists at all. And just as rivers on Earth carry water from the highlands to the seas, the cosmic filaments carry intergalactic gas from the more diffuse regions toward the dense knots, feeding the galaxy clusters and the galaxies within them. The whole cosmic web is in slow, constant motion, with gas flowing along the threads, drawn by gravity toward the points of greatest concentration. This flow has direct consequences for galaxies themselves. Galaxies do not exist in isolation. They are connected to the cosmic web through these streams of intergalactic gas. New material is constantly being delivered to galaxies by the filaments, providing fresh fuel for star formation. Without this delivery system, galaxies would slowly run out of the gas they need to form new stars, and they would eventually become red and dead, populated only by aging stellar populations. With the delivery system, galaxies can be replenished, at least for a while, allowing them to keep producing new generations of stars long after their original gas supply has been used up. The cosmic web is, among other things, the supply chain that keeps galaxies alive. You can think of a galaxy like our own Milky Way as a city, and the cosmic web is the network of highways and rail lines connecting that city to other cities and bringing in the resources the city needs to function. Without the highways, the city would be isolated. With them, the city is part of a much larger network of trade and exchange. The Milky Way sits on its own filament of the cosmic web. Other galaxies in our local neighborhood sit on the same filament or on adjacent filaments. Material flows between them slowly, over hundreds of millions of years, but flows nonetheless. The space between us and our galactic neighbors is not just a passive gulf. It is an active circulatory system. And the structure goes much larger than just our local neighborhood. Our local group of galaxies sits within a much bigger structure called the Virgo supercluster. The Virgo supercluster sits within an even bigger structure called Laniakea. Laniakea is a vast complex of superclusters and galaxy groups, all of which are connected by the cosmic web, all bound together into a single enormous cosmic neighborhood. And Laniakea itself is just one part of a much larger filamentary structure that astronomers have been mapping for the last several decades. The cosmic web extends as far as our surveys have been able to reach. Every galaxy we can see, no matter how distant, is part of this same fundamental architecture. Here is something extraordinary about Laniakea that most people never learn. The way astronomers discovered it was by tracking the motion of galaxies. When they carefully measured how galaxies in our region of space were moving, after accounting for the overall expansion of the universe, they noticed something strange. Almost every galaxy in our neighborhood, including our own Milky Way, was flowing toward a common point in the sky. Being pulled by gravity towards some vast concentration of mass that lies hundreds of millions of light years away. Astronomers call this mysterious region the Great Attractor. It is a dense gravitational basin at the heart of Laniakea, probably the combined gravity of enormous galaxy clusters sitting at the deepest point of our local supercluster. And right now, as you hear these words, our entire galaxy is falling toward it at something like 600 kilometers per second. 600 kilometers every second. We are not sitting still. We are in motion, along with every nearby galaxy, all being pulled together along the invisible architecture of the cosmic web. It is worth taking a moment to dwell on just how vast and intricate this structure really is. The observable universe contains roughly 2 trillion galaxies. Every single one of those galaxies is part of the cosmic web. Everyone sits on a filament, or in a cluster at the intersection of filaments, or perhaps as a lonely galaxy floating in the relatively emptier border regions near a void. There are no galaxies that exist outside the web. The web is the framework on which all visible matter is arranged. And the web extends with the same basic pattern of filaments and voids and knots across the entire visible universe, out to the very edge of what we can see. Beyond that edge, presumably, the same pattern continues. We just cannot observe it directly because the light from those regions has not had time to reach us yet. The largest known filaments in the cosmic web are almost incomprehensible in scale. Some of them have been traced for over 1 billion light years. To put that in perspective, our entire Milky Way galaxy is only about 100,000 light years across. A single cosmic filament can be 10,000 times longer than the diameter of our galaxy. Our galaxy, magnificent as it is a tiny droplet of light strung along an infinitely larger thread. And that thread is just one of countless threads making up the larger web. The scale staggers the imagination. The voids are equally extreme. Some of them are so large that they have their own names. There is the Boötes Void, sometimes called the Great Void, discovered in 1981. It spans about 330 million light years across. And within that enormous volume, there are only a few dozen known galaxies. To give you a sense of how empty that is, in a region of the cosmic web with normal density, that same volume would contain thousands of galaxies. The Boötes Void contains only a tiny fraction of what you would expect. It is essentially empty, as far as galaxies go. Just an enormous bubble of nearly nothing, surrounded by the bright filaments where almost everything lives. There are even larger voids. The KBC void, which our own Milky Way appears to sit in or near the edge of, may span well over 1 billion light years across. The exact size and existence of voids that large is still being debated and refined, but the general picture is clear. The universe has these enormous empty regions, and they are not rare. They make up the majority of cosmic volume. If you took a random point somewhere in the universe and looked around, the most likely thing you would find is that you were inside a void, far from the nearest filament, far from the nearest galaxy, surrounded mostly by darkness and the faint glow of the cosmic microwave background. This is one of the most important facts about the universe that almost nobody knows. Most of cosmic space is empty, not just thinly populated. Functionally empty, at least as far as galaxies and ordinary matter are concerned. The bright structures we can see, the filaments and the clusters, occupy maybe 1/5 or less of the total volume of the cosmos. The rest is voids. The universe is mostly absence, decorated with thin threads of presence. And yet, those thin threads contain almost everything. Every galaxy, every star, every planet, every living thing. All of it is concentrated along the filaments of the cosmic web. The voids are vast, but they are also vast emptinesses. The action, the matter, the structure, all of it lives on the threads. We live on a thread. Every star you have ever seen with your naked eye is part of our local thread. This is the architecture of the universe at the larger scales. Threads of matter woven through enormous voids of near emptiness. a web of light and gas and dark structure stretching as far as we can see. And the gas we discussed earlier, that warm, hot intergalactic medium that solved the missing baryons problem, is the visible signature of this larger web. It flows along the filaments, it pools in the clusters, it traces the architecture in plasma the way iron filings trace the lines of a magnetic field. By detecting that plasma and mapping where it lives, we are also mapping the cosmic web itself. The two are the same thing seen from different angles. Galaxies are points of light along the web. Plasma is the diffuse glow stretched between those points. Together they reveal the same underlying architecture. But we still have not answered the deepest question. Why do these filaments form in the first place? What gives the universe its preferred geometry? We have talked about gravity acting on tiny initial density fluctuations, and that is correct as far as it goes. But there is a deeper layer to the story, because gravity by itself, acting on ordinary matter alone, would not produce the cosmic web we see today. The math does not work out. If you simulate the evolution of the universe with only the visible matter, only the stars and gas and galaxies that we can detect, you do not get the right pattern of filaments and voids. You get something much more diffuse, much less structured, much less webby. To get the cosmic web we actually observe, you need something else. Something with mass. Something that exerts gravitational pull. Something that was present in enormous quantities in the early universe and that participated in the gravitational collapse that built the filaments. But something that does not interact with light. Something invisible. Something that cannot be seen by any telescope, no matter how powerful, because it does not emit, absorb, or reflect electromagnetic radiation of any kind. That something is the missing piece of the cosmic web. It is the unseen scaffolding that gives the visible structure its shape. It outweighs all the visible matter in the universe by a factor of more than 5-1. And without it, none of what we have been describing would exist. No filaments, no voids, no galaxy clusters, no web at all. The galaxies would be scattered much more evenly across space. The gas would not pool in the same patterns. The entire architecture of the cosmos would be unrecognizable. It is in many ways the most important thing in the universe, and we still do not really know what it is. But we know it has to be there. The cosmic web demands it. The mathematics requires it. And the more carefully we map the visible universe, the more clearly we see the gravitational fingerprints of this hidden material woven through every filament, every cluster, every void. To complete the picture of what fills the space between galaxies, we have to confront this invisible matter directly. We have to ask what dark matter actually is, how we know it is there, and how it shapes the cosmic web from behind a veil of total darkness. Because the visible universe, vast and intricate as it is only a fraction of what is really out there. The real architecture of the cosmos is largely unseen, and it has been waiting in the dark all along. We have spent some time now exploring the ghostly ocean of hot plasma that fills the spaces between galaxies, and the immense web of filaments and voids that organizes that plasma into rivers and pools across the cosmos. And if you have been following carefully, you may have noticed that there is something we have been quietly avoiding. Something that keeps lurking in the background of every explanation, every diagram, every model. Because every time astronomers try to explain why the cosmic web has the shape it does, why the filaments are arranged the way they are, why galaxies cluster in certain places and avoid others, The answer always involves gravity. And not just any gravity, not just the gravity of the stars and gas we can see. Something else, something invisible. Something that seems to be pulling on everything but cannot be detected directly. That something is dark matter. And to truly understand what fills the spaces between galaxies, we have to confront it. Because the entire cosmic web, every filament, every void, every cluster, every flowing river of hydrogen plasma sits on top of a hidden scaffolding made of this mysterious substance. The visible universe, all the stars and galaxies and gas, is essentially a thin coating of light, decorating an unseen skeleton. Without dark matter, none of the structure we see would exist. The web would collapse. The galaxies would never have formed. The universe would be a vastly different place. So, what is dark matter? Let us be honest, right at the start, we do not know. After almost a century of careful study, after some of the most sophisticated experiments ever conducted, we still do not have a definitive answer. We do not know what particles dark matter is made of. We do not know exactly how it interacts with itself. We do not know if it has any properties beyond gravity. What we do know with extraordinary confidence is that it exists, that it fills the universe in vast quantities, and that without it, almost nothing about the cosmos would make sense. The story of how we came to know this is one of the most fascinating detective stories in all of science, and it begins not with a search for invisible matter, but with a simple observation about how galaxies spin. In the 1930s, a Swiss astronomer named Fritz Zwicky was studying a cluster of galaxies called the Coma Cluster. He measured how fast the individual galaxies were moving relative to each other, and then he calculated how much mass the cluster would need to contain in order to hold all those fast-moving galaxies together by gravity. The math gave a clear answer. The cluster needed to contain far more mass than the visible stars and gas could account for. Many times more, in fact. Without that extra mass, the galaxies should have flown apart long ago. They were moving too fast to be gravitationally bound by the visible matter alone, and yet they were clearly bound. They had been orbiting each other for billions of years. Zwicky proposed that there must be some kind of invisible matter holding the cluster together. He called it Dunkle Materie, which is German for dark matter. The name has stuck ever since. But at the time, his idea was largely ignored. Astronomy was a small field. The data was uncertain, and most astronomers preferred to assume that there was some error in the measurements rather than accept the idea of vast amounts of unseen matter pervading the cosmos. It would take another 40 years before the dark matter hypothesis became impossible to ignore. In the 1970s, an American astronomer named Vera Rubin began studying how stars orbit within individual galaxies. Her work focused on spiral galaxies, including our own. The expectation was straightforward. According to the laws of gravity that we have known since the time of Isaac Newton, stars orbiting near the edges of a galaxy should move more slowly than stars near the center. This is the same principle that makes the outer planets of our solar system move more slowly than the inner ones. Mercury whips around the sun in just under 3 months. Neptune, far out at the edge, takes about 165 years to make a single orbit. The reason is simple. Gravity weakens with distance. The farther you are from the central mass, the slower you have to move to maintain a stable orbit. So when Rubin and her colleagues measured the orbital speeds of stars in spiral galaxies, they expected to find the same pattern. Stars near the center moving fast. Stars near the edge moving slowly. But that is not what they found at all. Instead, they discovered that stars at the edges of galaxies were moving just as fast as stars closer in, sometimes even faster. The orbital speeds did not drop off with distance the way they should have. They stayed roughly constant. This was so unexpected, so contrary to everything Newtonian gravity predicted, that at first it seemed like there must be a mistake. But the measurements were correct. They were repeated for galaxy after galaxy, by team after team using better and better instruments. And every time, the same strange pattern appeared. The outer regions of galaxies were rotating too fast. There was not enough visible mass to gravitationally hold those fast-moving outer stars in their orbits. The galaxies should have been flying apart, and yet they were not. Something was holding them together. Something invisible. Something massive. Something that extended far beyond the visible edges of the galaxies, surrounding them in vast unseen halos. Rubin's work, combined with similar measurements by other astronomers, made the case for dark matter overwhelming. Whatever this invisible substance was, it dominated the mass of every galaxy. The stars and gas we could see were just a small, bright fraction of what was really there. The bulk of each galaxy's mass was hidden in something that emitted no light, that reflected no light, that would not register on any telescope tuned to any wavelength. And the gravity of that hidden bulk was what kept the galaxies from tearing themselves apart. It is worth pausing to appreciate just how dramatic this realization actually was at the time, because the rotation curves Vera Rubin measured were not subtle. They were not noisy data that required complicated statistical arguments to interpret. They were stark, unambiguous, almost violent contradictions of what Newtonian physics demanded. Imagine you are an astronomer in the 1970s. You have been taught your whole career that gravity behaves a certain way. You have used those laws to land spacecraft on the moon, to predict eclipses centuries in advance, to calculate the orbits of asteroids with extraordinary precision. The mathematics works. It always works. And then you turn your telescope toward a spiral galaxy, and you measure how fast its outer stars are moving. And the answer comes back wrong. Not just slightly wrong, spectacularly wrong. The stars at the edge are moving so fast that, according to the laws you have built your entire scientific worldview on, they should be flying off into space. The galaxy should be unraveling before your eyes. But it is not. It is sitting there, perfectly stable, ignoring your physics entirely. Vera Rubin spent years carefully checking her measurements. She and her colleague Kent Ford developed extraordinarily sensitive instruments to make sure they were not making some kind of systematic error. They measured galaxy after galaxy. The same pattern appeared every single time. The outer regions rotated too fast. The discrepancy was not random. It was systematic. It was telling them something about the universe that nobody wanted to hear. Even after Rubin published her results, many astronomers resisted the conclusion. Some suggested that perhaps the laws of gravity simply worked differently on galactic scales. Others tried to invoke clouds of dim stars or cold dust that might be hiding from view. But every alternative explanation eventually ran into trouble. The dim stars would have been detectable by infrared telescopes. The cold dust would have left other signatures. None of the conventional explanations could account for the sheer amount of mass that needed to be invisible. By the 1980s, the dark matter hypothesis had gone from a fringe idea to the mainstream consensus, largely because of the patient, careful, undeniable work that Rubin and her colleagues had done. Now, this is already a pretty extraordinary claim, but the evidence for dark matter does not stop with rotating galaxies. It comes from many independent lines of investigation, all converging on the same conclusion. And one of the most striking pieces of evidence comes from a phenomenon called gravitational lensing. Gravitational lensing is a consequence of Albert Einstein's theory of general relativity. According to that theory, mass does not just pull on other masses through gravity, it actually warps the fabric of space and time itself. And when light passes through warped space, its path gets bent. So if you have a very massive object, like a galaxy or a galaxy cluster, sitting between you and a more distant light source, the gravity of the foreground object will bend the light from the background source. The result is that the distant object appears distorted. Sometimes it appears stretched into arcs. Sometimes it appears multiplied into several copies. Sometimes it appears as a complete ring of light around the foreground mass, what astronomers call an Einstein ring. The amount of bending depends on how much mass is doing the bending. So by carefully measuring how much the light from distant galaxies gets distorted as it passes through nearby galaxy clusters, astronomers can calculate how much total mass is in those clusters. And here is the punchline. When they do this, they find the same things Wiki found nearly a century ago. The clusters contain vastly more mass than the visible stars and gas can account for, roughly 5 or 6 times more. The lensing measurements agree beautifully with the rotation curve measurements. They agree with measurements of how fast galaxies move within clusters. They agree with measurements of the temperature of the hot gas-filling galaxy clusters. From every direction, every technique, every independent line of evidence, the same answer emerges. There is far more matter out there than meets the eye, and the discrepancy keeps coming back to the same staggering ratio. Perhaps the most spectacular demonstration of dark matter's existence comes from a remarkable object called the bullet cluster. The bullet cluster is actually the result of 2 galaxy clusters that collided with each other about 150 million years ago. As the clusters smash together, the hot gas in each cluster, which makes up most of the visible normal matter, got slowed down by the collision. Hot gas hitting hot gas creates friction and pressure. So the gas piled up in the middle of the collision zone, glowing brightly in X-rays. But the stars and galaxies, being much smaller and more spread out, mostly pass through the collision without slowing down significantly. They sailed right past each other and continued moving outward. Now here is the brilliant part. Astronomers used gravitational lensing to map out where the mass really was in this colliding system. And they found something extraordinary. Most of the mass was not where the hot gas was. It was where the galaxies were. Out on the wings, beyond the central pileup of glowing plasma, the mass had passed through the collision the same way the galaxies had, without slowing down, which meant that whatever this mass was, it could not be ordinary matter. Ordinary matter would have collided with itself the way the gas did, and ended up piled in the middle. The mass behaved as if it barely interacted with anything except through gravity. It was essentially invisible. It was essentially frictionless. It was, in every meaningful sense, dark. The bullet cluster is sometimes called the smoking gun of dark matter. Whatever is doing the gravitational pulling in those outer wings, far from the visible piled-up plasma, is not behaving like any form of ordinary matter we know of. It passed straight through the collision the way a ghost passes through a wall. So we know dark matter exists. We know it is everywhere. We know it dominates the mass of galaxies and galaxy clusters. We know it forms enormous halos that extend far beyond the visible stars and gas. But what is it actually made of? This is where the honest answer becomes, we do not know yet. But we do know what it is not. It is not made of ordinary atoms. We know this because the amount of ordinary matter in the universe is extremely well constrained by observations of the cosmic microwave background and by the abundances of light elements that were forged in the first few minutes after the Big Bang. Both of these measurements tell us that ordinary matter, the kind we are made of, accounts for only about 5% of the total energy content of the universe. Dark matter accounts for about 27%. The rest, about 68%, is something even stranger called dark energy, which we will not get into here because it is a different mystery entirely. But the point is, dark matter is not a missing form of ordinary matter. It is not faint stars we have failed to detect, or planets, or dust, or cold gas. It is something genuinely different. Some new kind of substance that we have never directly observed in any laboratory. For decades, the leading hypothesis has been that dark matter consists of some kind of new, fundamental particle. Something that exists outside the standard model of particle physics. Something that interacts only through gravity and possibly through the weak nuclear force, but not through electromagnetism, which is why it does not interact with light. Various candidate particles have been proposed. The most popular for many years was something called a weakly interacting massive particle, or WIMP. Another candidate is called the axion. Other ideas involve sterile neutrinos, primordial black holes, or even more exotic possibilities. Massive experiments are currently underway around the world to try to detect these particles directly. Deep underground laboratories shielded from cosmic rays are running incredibly sensitive detectors, hoping to catch the rare interaction between a dark matter particle and an ordinary atom. So far, despite decades of searching, no direct detection has been confirmed. The particles, if they exist, are even more elusive than we expected. This is a frustrating situation, but it is also a humbling one. The universe contains 5 times more of this mysterious stuff than it does of all the ordinary matter combined. And we still do not know what it is. The vast majority of matter in the cosmos remains, in a real sense, unknown to us. We are like people in a dark room who can feel the presence of furniture by bumping into it, but who cannot turn on the light to see what the furniture actually looks like. The experiments designed to find dark matter directly are some of the most remarkable scientific endeavors ever undertaken. Picture this. Deep beneath a mountain in Italy, or buried more than a mile underground in an abandoned gold mine in South Dakota, or tucked inside a tunnel deep below the surface in China, there are tanks. Enormous tanks, some of them holding tons of ultra-purified liquid xenon, cooled to extreme temperatures, surrounded by the most sensitive radiation detectors humans have ever built. These tanks sit beneath kilometers of solid rock, because the rock is needed to shield them from the constant rain of cosmic rays that bombards Earth's surface. Without that shielding, the experiments would be completely overwhelmed by ordinary background radiation. Even with the shielding, scientists must obsess over every possible source of contamination, every microscopic trace of natural radioactivity in the materials used to build the detectors, every faint signal from a stray cosmic ray that managed to penetrate the rock above. The hope is to catch a single dark matter particle as it passes through the tank and, by sheer chance, bumps into the nucleus of a xenon atom, transferring a tiny amount of energy that the detectors can register. The interaction would be so subtle, so fleeting, that distinguishing it from background noise requires extraordinary care. Teams of physicists have been running these experiments for decades. They have built bigger tanks, better detectors, more elaborate shielding. They have searched for years, and so far, they have found nothing. No confirmed signal, no detected particle, no direct evidence of what dark matter actually is. Consider what this actually means. We know dark matter exists. The astronomical evidence is overwhelming. The same matter we are searching for in those underground tanks is, at this very moment, passing through your body in enormous quantities. Vast numbers of dark matter particles are believed to be sweeping through your body every second, almost certainly without interacting with any of your atoms in any detectable way. We are bathing in this stuff. We are constantly being penetrated by it, and we still cannot see it. We cannot catch it. We cannot identify it. The most abundant kind of matter in our cosmic neighborhood remains, for now, completely invisible to every direct test we have devised. But even though we do not know what dark matter is made of, we have learned a great deal about how it behaves. And one of the most important things we have learned is that dark matter played the central role in building the cosmic web that we explored earlier. The filaments, the voids, the great walls of galaxies, all of it grew up around a scaffolding of dark matter that formed first, before the visible matter even had a chance to organize itself. Here is roughly how it worked. In the very early universe, just after the Big Bang, everything was extraordinarily smooth. The matter that existed, both ordinary and dark, was distributed almost perfectly evenly across all of space, but not quite perfectly. There were tiny fluctuations, microscopic variations in density from place to place. These fluctuations were not random. They were the seeds of all future structure. And over time, gravity went to work amplifying them. Dark matter began collapsing into denser regions first. Because dark matter does not interact with light, it was not affected by the radiation pressure that filled the early universe. Ordinary matter, by contrast, was constantly being jostled by photons. The pressure of all that radiation prevented ordinary matter from collapsing for hundreds of thousands of years. But dark matter, ignoring the radiation entirely, was free to start clumping under its own gravity from a much earlier time. By the time the universe had cooled enough for radiation pressure to drop and ordinary matter to start collapsing, the dark matter had already formed an elaborate framework. A scaffold of denser regions, surrounded by emptier regions, with filamentary structures connecting the densest knots. When ordinary matter finally started to collapse, it did not have to start from scratch. It fell into the gravitational wells that the dark matter had already prepared. The hydrogen and helium gas that filled the early universe streamed along the dark matter filaments. It pooled in the dark matter knots. It became the raw material for the first stars and the first galaxies, all of which formed in places where dark matter was already concentrated. Every galaxy you can see today, every spiral, every elliptical, every dwarf, sits inside a halo of dark matter that was there before the galaxy itself. The visible part of a galaxy is just the bright, glowing core of a much larger invisible structure. This means that when we look at the cosmic web of glowing galaxies and gas filaments, we are really looking at the visible markers of an underlying dark matter web. The filaments of galaxies trace dark matter filaments. The galaxy clusters sit at the densest dark matter knots. The voids are voids in the dark matter as well. The visible cosmic web is a kind of bioluminescent skin draped over a much larger and otherwise invisible dark body. The dark matter is the architecture. The galaxies and gas are the lights that let us see where the architecture is. Computer simulations have demonstrated this beautifully. By starting with the conditions that existed shortly after the Big Bang, with dark matter slightly clumpier in some places than others, and then letting gravity act for billions of simulated years, scientists have produced models of how dark matter should be distributed throughout the universe today. The results look remarkably like the cosmic web we actually observe. Long filaments, vast voids, dense knots at the intersections. The match between the simulations and the real observations is one of the strongest pieces of evidence that the dark matter framework really exists and really does behave the way the theory predicts. These dark matter halos are not small. The halo around our own Milky Way galaxy is thought to extend out to roughly 300,000 light-years from the galactic center, far beyond the visible disk of stars. Some estimates put it even larger. The total mass of the Milky Way's dark matter halo is something like 1 trillion times the mass of our Sun. By comparison, all the visible stars and gas in the Milky Way add up to maybe 1/10 of that. So when you think about our galaxy as a roughly 100,000 light-year wide spiral with a few hundred billion stars, you are thinking about only a small fraction of what the Milky Way really is. The galaxy you can see is just the bright innermost portion of a much larger invisible structure. Now, here is where things get interesting for our story about what fills the space between galaxies. Because if every galaxy has a dark matter halo extending hundreds of thousands of light years beyond its visible edge, those halos start to overlap with each other in the spaces between galaxies. The dark matter does not stop at any neat boundary. It fills in the regions between galaxies as well, and in the deeper intergalactic spaces, the dark matter is not concentrated in halos at all. It is spread out along the filaments, just as the hot gas is. The cosmic web of dark matter and the cosmic web of intergalactic gas are essentially the same web, just made of different substances. The gas traces the dark matter. The dark matter shapes where the gas can flow. The two are inseparable partners in the architecture of the universe. So when we ask what fills the space between galaxies, we now have a much richer answer than we did before. There is the hot diffuse plasma we discussed earlier. There is the cosmic web of filaments and voids, and underlying all of it, providing the gravitational skeleton that holds everything in place, there is the dark matter. Vast clouds of it, enormous halos around galaxies, long unseen ropes stretching between clusters, an entire shadow universe that outweighs the visible one by a factor of 5 or 6 to 1. It is worth dwelling for a moment on just how strange this is. For all of human history, when we have looked at the night sky, we have only ever seen the visible portion of the cosmos. The stars, the planets, the galaxies, the nebulae. And for thousands of years, we naturally assumed that what we could see was essentially everything that was out there. Maybe with some bits we had not noticed yet. But essentially, the universe was the universe of light. And then in the 20th century, we discovered that this is wrong. The universe of light is just a small, bright fraction of a much larger universe that we cannot see at all. The dark portion is not just bigger, it is dominant. It is the main component. The visible universe, the one we have been looking at and writing poetry about and naming constellations in for as long as humans have existed, is essentially a beautiful exception to the rule. Most of what is out there is invisible. We have just been too biased by our own visual nature to realize it. Now, a careful note here. We need to be honest about what we know and what we do not know. We know dark matter exists as a gravitating substance. The evidence for that is overwhelming. We know roughly how it is distributed, in halos around galaxies and along filaments connecting them. We know it dominates the mass budget of the universe. We do not, however, see it directly. Our maps of dark matter are not photographs. They are inferences. We deduce where the dark matter must be by observing how visible matter behaves under its gravitational influence. We watch how galaxies rotate. We measure how light bends around clusters. We map how galaxies cluster together. From all of these observations, we reconstruct what the dark matter distribution must be in order to produce the effects we see. The maps that result are accurate, in the sense that they reflect real underlying mass. But they are not direct images. We have never taken a picture of dark matter itself, because dark matter does not interact with light. There is no picture to take. We only see its shadow, so to speak, in the behavior of the matter we can see. This is an unusual situation in science. We are essentially doing astronomy on a substance that we cannot observe directly with any telescope. We can only see what it does to other things. But the effects are so consistent, so reproducible, so detectable across so many different kinds of observations, that we are quite confident the substance is real. We just do not yet know what it is fundamentally made of. It is one of the great unsolved mysteries of physics, possibly the greatest unsolved mystery, depending on how you count things. Some scientists have wondered whether dark matter might not exist at all, whether instead our understanding of gravity itself might be wrong. Maybe gravity behaves differently on the scales of galaxies than it does in our solar system. Maybe a modified theory of gravity could explain everything we see without requiring vast amounts of invisible matter. This idea has been explored seriously, and there are versions of it that can explain some of the observations. But none of the modified gravity theories currently proposed can explain everything as well as the dark matter hypothesis does. The bullet cluster, in particular, is very difficult for modified gravity theories to handle. So while the question is not completely settled, the dark matter hypothesis remains the strong frontrunner. Most cosmologists today believe that dark matter is real, even if its exact nature remains unknown. What we are left with then is a picture of intergalactic space that is extraordinarily different from the empty void it appears to be. There is hot diffuse plasma woven into a cosmic web. There is the underlying dark matter scaffolding that determines where the web can form. There are the connections between galaxies and the boundaries of voids. All of this, in some sense, is what fills the space between the galaxies. Not nothing, not emptiness, but an intricate, mostly invisible architecture that determines the entire structure of the visible universe. And yet, even with all of this, we have not quite finished our exploration. Because there's one more thing we have not talked about. The intergalactic medium is not just filled with matter, both ordinary and dark. It is filled with energy, with light, with radiation that has been traveling through it for billions of years. There are particles flying through it at nearly the speed of light. There are magnetic fields threading through it, weak but real. There is the faint afterglow of the Big Bang itself, still bathing every cubic centimeter of space including the deepest, darkest gulfs between galaxies. The space between galaxies is not just a passive container for matter. It is an active environment, alive with energy, constantly stirred by signals from across the cosmos. And to truly complete the picture, we have to take a closer look at what that energy is, where it comes from, and how it makes the great voids between galaxies feel a little less like emptiness, and a little more like the vast humming nervous system of the universe itself. So here we are. We have explored the ghostly ocean of hot plasma that fills the void. We have traced the cosmic web of filaments along which everything is organized. We have peeled back the visible universe to reveal the invisible scaffolding of dark matter that shapes the entire architecture. And by now, the intergalactic gulfs between galaxies should look very different to you than they did when we started. Not empty at all. Filled with hidden matter, threaded with structure, sculpted by gravity. But there is still one more layer to this story. And in some ways, it is the most surprising layer of all. Because intergalactic space is not just a quiet container holding all of this matter in place. It is alive with energy. It is humming with radiation. It is crisscrossed by particles traveling at nearly the speed of light. It is threaded by magnetic fields whose origins remain one of the great unsolved puzzles in cosmology, and bathing every single cubic centimeter of it, no matter how deep into the voids you go, no matter how far you travel from any galaxy or cluster or filament, there is the faint, warm afterglow of the Big Bang itself. A whisper of light from the very beginning of time, still flowing through every corner of space, still detectable, still carrying information about how everything began. The space between galaxies is not silent. It is the most active environment in the universe. It just happens to be active in ways that we, with our biological eyes, adapted to a narrow sliver of the electromagnetic spectrum and a planet full of noise, cannot easily perceive. To understand intergalactic space at the deepest level, we have to learn to listen for what is actually flowing through it. And the first and most important signal, the one that fills literally every direction we look, is the light from the Big Bang. Imagine you could shrink down to the size of an atom and float in the middle of the deepest void in the cosmos. Light years from any galaxy. Light years from any filament. Surrounded by what feels like absolute darkness in every direction. And then imagine you had a special instrument that could detect microwaves. Long wavelengths of light that human eyes cannot see. If you turned that instrument on, you would discover something astonishing. The darkness around you is not dark at all. It is glowing, faintly, evenly, in every direction you point your detector. There is light coming from everywhere, not from any star, not from any galaxy, from space itself. This is the cosmic microwave background, and is one of the most important discoveries in the history of astronomy. It is the cooled down remnant of the radiation that filled the universe when the cosmos was only about 380,000 years old. At that time, the universe was so hot and dense that it was filled with a kind of glowing plasma. Light could not travel freely. It kept bouncing off charged particles before it could go anywhere. The universe was opaque, like the inside of a thick fog. And then, after about 380,000 years of expansion and cooling, the temperature dropped low enough that electrons could finally combine with protons to form neutral hydrogen atoms. Suddenly, the fog cleared. Light could travel freely for the first time, and the radiation that was present at that moment, the light from that primordial fog, began streaming outward through the universe, in every direction, from every point, That radiation has been traveling ever since, for nearly 14 billion years. It has been stretched and cooled by the expansion of space, so that what was once visible light has shifted into long microwaves with a temperature of just under 3 degrees above absolute zero. But it is still here. It still fills every cubic centimeter of intergalactic space. Right now, as you sit there listening to this, microwaves from the early universe are passing through your body, through the room you are in, through the planet beneath you, through every cubic meter of the deep voids between galaxies. The cosmic microwave background does not avoid the empty spaces. It is most prominent in the empty spaces because there is nothing there to absorb it or scatter it. The voids that look so dark to our eyes are actually flooded with this ancient light. They are the brightest places in the universe in microwave wavelengths. We just cannot see it without specialized instruments. When astronomers turn those instruments toward the deepest, darkest patches of sky, they find this glow everywhere. Astonishingly uniform. The temperature varies by only about 1 part in 100,000 from one direction to another. Those tiny variations are the seeds of all later structure, the same primordial ripples that grew into galaxies and clusters and the cosmic web itself. So when we look at the cosmic microwave background, we are looking at a baby picture of the universe, frozen in microwave light, filling every corner of intergalactic space. A constant whispered reminder that the cosmos has a beginning, and that the echo of that beginning is still all around us, even in the places that look the emptiest. But the cosmic microwave background is just the loudest of many signals flowing through the void. There is also another, more complicated kind of light that fills intergalactic space. Astronomers call it the extragalactic background light. And it is the combined glow of every star, every galaxy, every quasar, every active galactic nucleus, every flickering source of light that has ever existed in the universe, all merged together into a faint diffuse radiation. Some of that light is in the optical range, what our eyes would see. Some is in the infrared. Some is in the ultraviolet. Some is in even more energetic wavelengths. All of it has been traveling through the void for millions or billions of years to reach us. And all of it is constantly passing through the spaces between galaxies in every direction. Think about what that means. Every photon that has ever been emitted by a star somewhere in the universe, if it did not get absorbed along the way, is still out there flying through space. The light from the first generation of stars that formed when the universe was only a few 100 million years old is still traveling. Some of it is reaching us now. Some of it has already passed us and is heading farther outward. Some of it is bound for galaxies we will never observe. The intergalactic medium is constantly being washed through by this diffuse rain of light from every era of cosmic history. The void between galaxies is, in this sense, the largest illuminated space in existence. It just happens to be illuminated so faintly by sources so far away that the brightness at any one spot is barely above the threshold of detection. When you start to think about it this way, the deep intergalactic dark begins to feel almost crowded. Photons from billions of years ago. Photons from billions of light years away. Photons from quasars that died long before our solar system was born. All of them streaming through the same volumes of empty space, mostly without ever interacting with anything, mostly without ever being noticed by anything, just continuing their ancient journeys forever. Or until they happen to fall into the lens of some telescope or the eye of some observer. The void is a place of perpetual silent traffic, a vast superhighway of light that nobody can really see except by accident. And there is more. Because not only are there photons everywhere out there, but those photons sometimes carry information about what they pass through on their way to us. This brings us to one of the most clever techniques in modern astronomy, something called the Lyman alpha forest. The name sounds strange, but the idea is beautiful. When light from a very distant quasar travels toward Earth, it passes through enormous numbers of intergalactic hydrogen clouds along the way. Each cloud absorbs a tiny bit of the quasar's light at a very specific wavelength. By the time the light reaches our telescopes, it carries the imprint of every cloud it crossed. When astronomers split that light apart and analyze its spectrum, they see a forest of dark absorption lines, each one corresponding to a different cloud of hydrogen at a different distance along the path. By reading the pattern of those absorption lines, astronomers can effectively map out the distribution of intergalactic hydrogen clouds across billions of light years of space. Clouds that will be otherwise invisible. Clouds that emit no light of their own. Revealed only because they happen to lie in front of a brilliant background source. This technique has revolutionized our understanding of intergalactic space. The Lyman alpha forest has shown us that the void is filled with countless faint hydrogen clouds at every distance. They are part of the cosmic web. They trace the filaments. They give us a three-dimensional map of where the gas is and how it is moving. And they remind us, once again, that the deep, dark gulfs we see when we look up at the night sky are not actually empty. They are crowded with material that simply does not glow brightly enough to be seen on its own. We only catch sight of it when something brighter shines through it from behind. So far, we have talked about light flowing through intergalactic space, but there is another kind of messenger out there. Something far more energetic than ordinary photons. Particles. Real physical particles, mostly protons and atomic nuclei, traveling through space at almost the speed of light. They are called cosmic rays, and the highest energy among them, the so-called ultra-high energy cosmic rays, are some of the most extreme objects in the universe. These particles carry energies that are astonishing by any human standard. A single ultra-high energy cosmic ray can pack as much kinetic energy as a fast-pitched baseball. But all of that energy is concentrated into a single subatomic particle. The amount of energy per particle is so absurd that it took physicists a long time to convince themselves the measurements were real. We still do not fully understand where these particles come from. We know they originate outside our galaxy, somewhere in the deeper cosmos, probably accelerated by enormously violent processes near supermassive black holes, or in the shocks of colliding galaxy clusters, or in some other extreme environment we have not yet identified. They travel through intergalactic space for millions or billions of years before, occasionally, one of them happens to slam into the upper atmosphere of Earth, where it produces a shower of secondary particles that we can detect with vast arrays of ground-based instruments. The remarkable thing about these particles is that they can travel across enormous intergalactic distances without losing all of their energy. The void between galaxies, for all its faint plasma and its hidden hydrogen clouds, is empty enough that even an extremely energetic particle can fly through millions of light years before encountering anything substantial. Most cosmic rays simply travel through the dark for inconceivable amounts of time, occasionally being slightly nudged by magnetic fields. occasionally losing a small fraction of their energy through interactions with the cosmic microwave background, but otherwise just sailing onward. The intergalactic medium is the highway they use to travel from one part of the universe to another. The fact that this highway works, that particles can actually cross such distances and still arrive at Earth with enormous energies intact, is one more piece of evidence for just how genuinely empty the deep void is. Empty enough to be transparent to even the most extreme natural projectiles in existence. But cosmic rays are not the only particles streaming through intergalactic space. There is something even stranger flying through the void. A particle so elusive, so ghostly, that it makes everything else we have discussed seem almost solid by comparison. Neutrinos. Almost massless particles that interact with ordinary matter so weakly that they can fly through the entire Earth without hitting anything. Right now, as you sit there, trillions of neutrinos are passing through your body every second. Almost all of them coming from the sun, but some of them come from much farther away. From supernova explosions in distant galaxies. From the violent cores of active galactic nuclei. From catastrophic events billions of light years away. Neutrinos travel through intergalactic space almost entirely without obstruction. They do not get scattered by magnetic fields. They do not lose energy to intergalactic gas. They do not get absorbed by hydrogen clouds. They just fly, in perfectly straight lines, through millions or billions of light years of cosmic space, carrying information from the deepest, most violent processes in the universe to anyone sensitive enough to catch them. Catching them is extraordinarily difficult. Because neutrinos interact so weakly with matter, you need enormous detectors to have any hope of registering them. The largest neutrino observatory on Earth is called IceCube. It is buried deep in the Antarctic ice sheet, a cubic kilometer of clear polar ice, instrumented with thousands of light sensors, watching for the tiny flashes that occur in the rare moments when a neutrino from space happens to collide with an atom in the ice. IceCube has been operating for years, and it has already caught neutrinos that could only have come from outside our galaxy, from distant objects called blazars, where supermassive black holes are firing jets of material almost directly at Earth. Messages from across the cosmos, written in particles that pass through billions of light years of space without so much as flinching. And there is more. In addition to these high-energy neutrinos from violent sources, there should be a background of neutrinos from the Big Bang itself. Released when the universe was just 1 second old, even earlier than the light of the cosmic microwave background. That primordial sea of neutrinos is still out there, filling every cubic centimeter of space, far below the threshold of what any current instrument can detect. But it is there, every bit as real as the microwave background, and much older. And speaking of magnetic fields, this brings us to one of the most surprising features of intergalactic space. For a long time, astronomers assumed that the deep voids between galaxies should be essentially free of magnetic fields. Magnetic fields, after all, are typically generated by moving charged particles, by spinning stars, by the dynamos at the cores of planets and galaxies. In a region with almost no matter, what could possibly generate a magnetic field? And yet, when astronomers started looking carefully, they found magnetic fields everywhere. Not strong ones, by any earthly standard. We are talking about field strengths that are millions or billions of times weaker than the magnetic field of Earth. Almost impossibly faint. And yet present, more or less consistently, even in the deepest intergalactic voids. The way astronomers detect them is by looking at how light from distant sources gets affected as it passes through magnetized regions. Magnetic fields can rotate the polarization of light. They can affect the propagation of cosmic rays. They can leave subtle signatures in the radio emission from distant galaxies. By stitching together many different observations, astronomers have built up a picture of an intergalactic universe that is gently but pervasively magnetized. Where do these fields come from? This is a real puzzle. One possibility is that they were generated in the very early universe, perhaps during inflation or during some other primordial process, and have simply persisted ever since, slowly amplified or stretched by the expansion of space. Another possibility is that they were generated more recently by galaxies and active galactic nuclei, blown outward by powerful jets and stellar winds, gradually filling the surrounding intergalactic regions with weak magnetism over billions of years. The truth probably involves a combination of both processes, but the bottom line is that intergalactic space is not magnetically empty. There is a faint magnetic field essentially everywhere. The void is not magnetically dead. It hums very softly, with a kind of universal magnetism that we are only beginning to understand. And these intergalactic magnetic fields, faint as they are, actually matter. They affect how cosmic rays travel through space. They influence how plasma flows along the cosmic web. They may have played a role in the formation of the first galaxies by shaping how gas could collapse and how stars could ignite. They are part of the active life of the void, even though their direct effects are subtle. So now, finally we can put the whole picture together. Let us step back and try to see all of it at once. What does the space between galaxies actually contain? It contains the warm, hot, intergalactic medium, that ghostly ocean of thin plasma that we discussed at the beginning. The bulk of all ordinary matter in the universe, spread so thinly that it would feel like vacuum to any human instrument, but adding up across cosmic volumes to outweigh all the visible matter inside galaxies combined. It contains the cosmic web, the great filamentary structure along which all matter is organized, the largest known pattern in existence, a vast network connecting every galaxy to every other galaxy through threads of plasma and dark matter. It contains the dark matter scaffolding, the invisible skeleton on which the visible universe is draped, 5 or 6 times more massive than all ordinary matter, completely transparent to light, detectable only through its gravitational effects. The substance that holds galaxies together, that built the cosmic web in the first place, that we still cannot directly identify after nearly a century of searching. It contains the cosmic microwave background, the cooled down afterglow of the Big Bang, filling every cubic centimeter of space with faint microwave radiation that has been traveling for almost 14 billion years. It contains the extragalactic background light, the combined glow of every star and galaxy and quasar that has ever existed, streaming through the void in every direction. It contains the Lyman alpha forest of hydrogen clouds, traceable through their shadows on the light of distant quasars. It contains ultra-high energy cosmic rays, particles flying through the void at nearly the speed of light, carrying energies that defy easy comprehension. And it contains intergalactic magnetic fields, weaving faintly through everything, weak but pervasive, mysterious in their origins. That is what fills the spaces between galaxies. That is what is actually there in those black gulfs between every shimmering island of stars. Not nothing, not empty space. A vast, attenuated, intricately structured environment that is, in some ways, the largest and most architectural feature of the entire cosmos. The galaxies are the bright decorations. The intergalactic medium is the stage on which everything happens. It is worth dwelling on the strangeness of this for a moment, because for most of human history, we did not know any of this existed. We looked at the sky, and we saw stars and dark spaces between them. We assumed the dark spaces were just absence, just nothing. We had no reason to think otherwise. There was no way for an unaided human eye to detect the warm, hot intergalactic medium, or the cosmic microwave background, or the dark matter halos extending around every galaxy, or the cosmic web of filaments organizing everything. All of this was invisible to us for thousands of generations of human existence. We only learned about it in the last several decades, through some of the most sophisticated scientific instruments ever built, through telescopes in space, through detectors deep underground, through massive computational simulations, through painstaking observation and analysis spanning the careers of thousands of scientists. And what we have discovered is that the universe we thought we lived in, the universe of stars and galaxies floating in empty darkness, was a misleading picture. The real universe is a place where empty darkness is the exception, not the rule, where the spaces between things are filled with substance and structure and energy, where the apparent emptiness of the deep void is actually one of the busiest, most architecturally complex environments in existence, where the bright glowing galaxies we love to photograph are not the main story, but rather the small visible signatures of a much larger and mostly invisible cosmic order. This changes how we should think about our place in the universe. We do not live in a galaxy floating alone in the dark. We live in a galaxy embedded in a halo of dark matter, sitting on a filament of the cosmic web, surrounded by hot intergalactic plasma flowing along that filament, bathed in the cosmic microwave background, crossed by cosmic rays, threaded by faint magnetic fields, illuminated by the combined glow of every other galaxy in the visible universe. The dark spaces between us and our nearest cosmic neighbors are not separating us from them. They are connecting us to them, through gravitational filaments, through flowing gas, through dark matter scaffolding, through ancient light that has been traveling between us for billions of years. The cosmos is not a collection of isolated islands. It is a single, vast, connected structure. And the so-called empty spaces are the connective tissue that makes the whole thing one thing, instead of many. There is something humbling about this, and there is something also strangely uplifting. Because if the void between galaxies is not really empty, if it is full of hidden architecture and ancient signals and unseen matter, then the universe is far richer than we ever imagined when we just looked at the bright spots. We have only just begun to perceive what is actually out there. We have built telescopes that can detect the cosmic microwave background. We have built X-ray observatories that can pick up the faint glow of intergalactic plasma. We have built gravitational lensing surveys that can map the dark matter scaffolding. We have built cosmic ray detectors that can catch ultra-energetic particles arriving from the depths of space. With each new instrument, with each new technique, we see a little more of what was already there. The universe has been waiting for us to develop the tools to see it. And the more tools we develop, the more crowded and active the void becomes. But what is already clear is this: The space between galaxies is not nothing. It never was. It only looked like nothing because we did not have the means to see what was really there. Now we do, at least partially. And what we see is a universe that is far more interconnected, far more structured, far more alive with hidden activity than the simple picture of stars in a void ever suggested. So the next time you look up at the night sky on a clear dark night, and you see those great patches of black between the few thousand stars visible to your eyes, try to remember what is really there. There is hot plasma flowing along filaments. There is dark matter shaping the architecture of everything. There is the cosmic microwave background filling every direction with the cooled down light of the early universe. There are cosmic rays flying through the void at nearly the speed of light. There are magnetic fields humming faintly through everything. There are photons from distant galaxies that have been traveling for billions of years, just now arriving at the patch of sky you happen to be looking at. The dark spaces are not really dark. They're crowded with signals and structures and history. They are the largest, faintest, most architectural environment in the universe, and we are part of it. We always were. We just had no idea. In the end, maybe the most beautiful realization is that the cosmos does not have empty places, only places we have not yet learned to see. The voids that look so absolute to our unaided eyes are full. The gaps that seem to separate galaxies are actually the threads that connect them. The darkness between everything is not the absence of universe. It is the universe, quietly carrying on with its work in the wavelengths and substances and energies that lie just beyond our ordinary perception. And as we continue to build better instruments and better theories, as we continue to explore the deep places between things, we will keep discovering that the universe is bigger and stranger and more wonderful than we knew. Not because there is more out there than we thought, but because what was always out there has been waiting for us to notice. The space between galaxies is not nothing. It is everything we have not yet looked at carefully enough. And it has been there all along, holding the entire cosmos together, in the dark. Good night. And the next time you look up, remember, the void is full.